Momentum and Rotation Review 9. A thin ring is suspended from the ceiling with a string that is wound many times around the ring. The ring is released from rest. Derive expressions for the tension, the acceleration, and the angular acceleration. To do that, I think we should draw a free body diagram of this ring. Let's do that. mg for the ring is going to act at the center of mass of the ring. Even though there's no physical bit of the ring that is right there, mg will act as if it's at the center of mass. And then we have the tension in the string trying to hold this ring back. If we sum the forces up and down, down is going to win this whole battle. So I'm going to say that down is positive. So I'm going to go mg minus t. And according to Newton's second law, that should equal the mass of this object times its acceleration. So there's one equation. Why don't we then sum the torques about the center of mass? If we do that, mg doesn't contribute any torque. It's only the tension that's going to contribute torque, and that's the force, and then R is the lever arm. The net torque should equal the moment of inertia of this ring times alpha. Now, the moment of inertia for a ring, we actually derived this in a video, but more likely you'll just look it up somewhere, is mr squared. And we've talked several times how alpha can be rewritten as A over R. What does this expression simplify to? I'm seeing that R cancel one of those, and then that R canceling that R. So I'm seeing tension is equal to M times A. If tension equals M times A, then I can put M times A in right there. Here we go. Do I have room on my screen? mg minus ma equals ma. M's cancel. And what is the acceleration? The acceleration is going to be 1/2 g. The tension, let me write it over here. The tension is m times a, so the tension is 1/2 mg. And what about alpha? Alpha right here is a divided by r, so that's going to be 1/2 g over r. That's what you've got there. Suppose we do the same thing, but now we have a disk. Now the only difference here is that the disk is going to have a moment of inertia. Again, you can look this up, which is 1/2 mr squared. So we'll do the same thing. We've got a free body diagram. I've got mg acting down like that. I've got the tension acting up like that. Here we go. Let's sum the forces vertically. mg minus the tension should equal the mass of this thing times its acceleration. The net torque about the center of mass, tension times r, is equal to the moment of inertia, 1/2 mr squared, multiplied by alpha. As we just said, alpha is the same thing as a over r. So what does this expression simplify to? All the r's cancel. I'm seeing that the tension is equal to 1/2 ma. Let's put that in here. If the tension is 1/2 ma, let's put that into the first equation. mg minus 1/2 ma equals ma. The m's cancel. With that 1/2 on this side, that'll give you 3/2. So I think in this case, a is going to be 2/3 g, which means alpha is going to be 2g over 3r. And what's the tension going to be? Let's put 2/3 g in right there. The 2's will cancel. I think the tension then will be 1/3 mg. So what we're finding is for the disk, and I get all of these on one go. It's not easy, but there we go. For the disc, which is the one on the bottom, the tension is less. For the ring on top, the tension is more. The acceleration is more for the disc. The acceleration is less for the ring. So let's answer these last questions by circling the right answer. Which object would hit the floor first? That's going to be the disc. The other one, remember, is only accelerating at 1/2 g. So the disc is going to hit the floor first. Which one would the string be more likely to snap? The string's tension for the disc is 1/3 mg. For the ring, it was 1/2. That's a bigger one. 1/2 is bigger than 1/3. Which one has a larger net force? Well, the one that has a larger net force is the one that has the greater acceleration. And we said that the disc has a greater acceleration. It's 2/3 g compared to 1/2 g for the ring. Which one is there a larger net torque on the object? Well, what's the net torque? The torque is, can we find it right here? Right there. The torque is just the tension multiplied by the radius. The radius is the same for each case. So the one with the larger torque is going to have a larger tension. And the tension in the string when we had the ring was 1/2 mg, which is bigger than 1/3. So which one has a larger net torque? The ring has a larger net torque.